Hello, everyone. Welcome to this Wind Power Engineering Development webinar, Condition Monitoring Systems, Innovation and Technology, Shaping the Future of Turbine Maintenance. I'm your host, Nick Sharpley, Associate Editor of Wind Power Engineering and Development magazine. Thank you for joining us. This webinar is sponsored by EDF Renewable Energy. Just a brief agenda before we start. This webinar will be available at windpowerengineering.com. A link to it and the slides will be emailed to everyone. And at the end of the presentation, we'll have a question and answer session. Of course, not everyone who wanted to watch today's webinar could do this, but you can help them learn from it by tweeting key points and takeaways you think are important. In your tweets, be sure to include the hashtag WinWebinar. After the presentations, I'll read the questions that you and the audience have submitted. You can do this by typing them into the questions box on your GoToMeeting panel that should be on the right of your screen. We'll try to answer as many as possible before the hour is up. Let me tell you a little bit more about our speakers, and then I'll turn the microphone over to them. Jeffrey Weiner is the Global Sales and Commercial Manager for GE Wind Services. Mr. Weiner received his mechanical engineering degree and has worked at GE for over 30 years in several divisions. He started his GE career as a field engineer working on steam and gas turbines in the central U.S., then spent 11 years in GE aircraft engines, where he rose from test engineer to manager of the Military Development Test Facility. In 1993, he became the manager of the combustion labs and spent several years in the GE Industrial before returning to GE Power in 2000 as the global sales director for the GE Hydro. Joining GE Wind in 2004, Mr. Weiner leads the rapidly growing wind services business at their renewable energy headquarters. Ross McKellar is the Senior Vice President of Monotech, Inc. Mr. McKellar gained his master's degree in electrical and reliability engineering in 1975 in Sydney, Australia, and has since worked as both an electrical engineer and mechanical engineer. He has been working in the maintenance arena for the last 46 years, spending the first 16 years in the Australian airline industry, where he ultimately specialized in reliability engineering and was involved in the implementation of maintenance philosophies and concepts, which are now referred to as reliability-centered maintenance. With that, let's start. Jeff, the microphone is yours.
Hi, everybody, and thank you for taking the time out of your busy schedules to listen to this webinar today. The topic here is about condition monitoring systems, and while that's a very broad topic, I really just want to speak to a couple aspects of that, and specifically about how condition monitoring systems, and as they become more prevalent in wind turbines, start to enable other technologies. Now the first one I have to click. There we go. My apologies. So first off, I think everybody in the industry wants to understand how condition monitoring systems, really the ultimate goal is how can you lower costs or increase life of your units. Really, how does it impact your financials? And it's a very simple equation that actually, before you can even start to understand the cost implications and aspects of a CMS systems, you have to understand your turbine's health. And for that reason, while GE certainly does sell CMS systems, my point of my presentation is not necessarily to talk about any one CMS system or either methodology, but really just to talk about what the systems do. So highly recommended, and I will say that on any unit that General Electric has the operations and maintenance under what we call our full service agreement. Included in that is a CMS system, because we believe the best way to mitigate risk is to know about risk up front, so that you can be proactive instead of reactive. So, as I mentioned, CMS is really an enabler. It can help you turn unplanned maintenance into planned maintenances. It has great opportunities for you to monitor and optimize the scheduling of resources at a site, parts planning, so that you can really, if you know something has to be replaced, or a part, a gearbox, or a part of a gearbox at a certain time, that you can make sure that you get the capital parts or other flow parts that's required to support the outage. Moving a little bit more towards a thermal model. And then the last one there, where it enables up-tower repairs. Certainly from my perspective and the GE perspective, we think that one of the next revolutions in the wind industry really is up-tower repairs, because the major maintenance events that we've all seen happen around gearbox, generator, shafts, and other aspects, the most expensive part of that maintenance, and I'll show you some numbers in a few minutes, but clearly is the crane. And if we can minimize the amount of time that a crane is necessary, or even if a crane is necessary, or even just reduce the size of the crane, that can have impacts upon the overall cost of maintenance. So if CMS is an enabler, it's a question of how you, as an owner or operator, how are you going to use it? So as you can see, where we're going to focus the rest of the presentation is on that last bullet about how it enables up-tower repairs. So just some backgrounds about gearbox repairs, which is probably the most highest visibility repair that we have in the wind industry right now, and certainly has been a factor on older units. I'd like to think it's getting better as the industry and the gearbox designs become more advanced, but it's certainly an issue for the installed base industry. On GE units, we can see that O&M costs can run up to as high as 60%, could be associated with really the drivetrain, not just the gearbox. And that could have an impact of 1 to 2% upon AEP impact of the drivetrain repairs. Our approach, summarized on the bottom of this page, is primarily that we have a system that we call Pulse Point, and I'm sure other folks have other systems and processes. But Pulse Point is a combination of both SCADA data usage as well as the vibration data from a CMS system. The GE CMS system uses 6 accelerometers located across the drivetrain. So with things we call anomaly detection, where we look for certain outliers, where we do proactive parameter changes. But those types of things are how we try to predict potential problems in a gearbox. And of course, once we do, it generally triggers an inspection. Monitoring is great, and what we see electronically is fabulous, but it doesn't replace having someone up a tower see and validate something and put an eyeball on it also. And the whole idea really with up-tower repairs is really to do as much work up-tower and replace only the damaged components, not run to failure because you had predictive indications from your CMS system that told you there was a problem. So the earlier you can catch things, let's use that time to reduce the repair cycle costs. There are a lot of benefits of up-tower repair. Obviously, lower material costs because you're only replacing those components. The crane, and just understand that just because there is an up-tower repair doesn't mean that a crane is never necessary, but it can minimize the amount of time a crane is necessary, and it can minimize the size of the crane. Outage times can be reduced, outage times can be adjusted, outage times can be planned. Outage times can be tied to when other units are going to be down, so you maximize both specialized crews, the crane, and other resources, with the goal ultimately of extending the component life and keeping costs down. So let's talk a little bit about when I use the term up-tower repair, what kind of repairs are we talking about? And what you see is a cutaway of a typical 3-stage gearbox there. So you have a low speed section, you have an intermediate speed, and you have a high speed section there. And our industry in general has gotten much better about high speed repairs and even intermediate speed repairs. There's been a wider range of applicability of these and demonstrated capabilities and parts availability to do high speed and intermediate both pinion, shaft, bearing replacement. The low speed area is a much tougher component just because of the way. If you think about it, most gearboxes, when they're assembled in a factory, are actually assembled on the vertical, are set on their end and assembled vertically, whereas in the cell, all of a sudden now you just can't turn the gearbox necessarily on its vertical, so you have to develop tooling, procedures, and other methodologies for validation to be able to essentially take the gearbox off at the horizontal split point. And I also want to highlight that while it sounds easy, an up tower repair, just even replacing a high-speed shaft, bearing, something like that, or intermediate speed, um, this is kind of like doing open heart surgery outside in a tent on the top of a pole, 80 meters high. It's not simple. It requires a tremendous amount of cleanliness. It requires a certain amount of new procedures that are being built. This is not just maintenance that anybody or any inexperienced crews can do. So before you do have any up tower repair done, please make sure you understand the experience level of the folks that are going to do it for you. Make sure they've done this before. And it gets even more complicated because while we all know there's a lot of, at least from a GE perspective, a lot of Winergy gearboxes out there, there are several different manufacturers of gearbox. And the repair procedure to take down a Bosch, a Rexroth, or a GE, a Getz, or others can be significantly different procedures than taking down one of the other ones, or a Winergy. So just because one company may have some expertise in one brand doesn't necessarily mean it has expertise in all brands. So, or nor have the specialized tooling that may be necessary because each unit also requires some specialized tooling and procedures. So this is complicated stuff, but its capacity to have an impact upon the industry, I think, is tremendous. So I constantly believe in sharing some data with the industry. And while understand the numbers that I have up here because of whose gearbox it is, where it's located, whether it's in Canada, America, even various parts of the country are different. But I want to show you what the potential impact of this can be. So, and again, I'm speaking for a GE unit, so obviously if you Clipper gearboxes with 4 generators or other configurations or things are different, but for a GE unit, a traditional gearbox replacement literally can run in the range of $300,000 to over $400,000 for the cost of the gearbox, the crane, the labor to put it up. We do have some other options, and I think others also have, is where they can use various types of fixturing so that you don't have to drop the rotor to change out a gearbox, and that may be able to reduce it by $100,000 or a little bit less, if possible. But if you look at up tower repair on the bottom, so you can see for a high-speed shaft, this could be in the range of under $50,000, and even for an intermediate speed shaft, it can be in the range of under $100,000. So you can see that if you can have the proactive data analysis from the CMS system, if you develop those strong routines, and I think Ross is going to talk more about CMS systems and their capabilities of how to detect it. My point is that using that data can make a huge impact upon your operational costs. CMS, we truly believe, is one, and the technologies that it will enable can really be a turning point for the wind industry, and is a way that we will compete in a non-subsidy world, ultimately. Okay. So I said earlier that it's a very complicated space, up tower repair, and as you can see, this is just a few areas that there are so many different configurations of both designs, and I by no means have all the designs listed here on the left-hand side, but I just have about 6 or 7 of them, a few different manufacturers. You can see the differences in models. Each of those require different capabilities, different skill sets, like that. And really the biggest challenge for our industry going forward, at least from an up tower repair capability, is going to be the issue of taking on the low speed and the planetary sections. This can be done, this will be done. There are some people that are already doing some elements of it now. And we, GE, are also working on expanding that capability into those sections, because we know that some of the planetary gears are also on certain models are showing a higher than normal, or I shouldn't say higher than normal, have experienced a number of failures. So it's a key area for us to develop. I think that the industry as a whole is really just at the beginning steps of up-tower repair right now. Um, and we look forward in GE, we are investing uh, time, effort, and money into up-tower repair. We own no crane companies in GE, and we'd rather spend our money on technology development that helps lower costs for owners. Uh, the other reason, I guess, that we are incentivized to do this from a GE perspective is that we are the operator through our full service agreements where we take bumper to bumper responsibility for the cost. We are also vested in finding lower ways to maintain our units because ultimately having our full service agreement and us taking that risk from customers, it's the best way for us to improve our risk situation also is by finding lower cost ways to maintain units. And CMS is going to do that for us. It's not only a question of moving to up-tower repair, but ultimately the industry will move to a more predictive-based maintenance, condition-based, that some units on a farm may need to be maintained more frequently than others just because of where they are in the wind stream, impacts of waking effects or other aspects. But why take them all down at the same time when you could vary their response times, vary their maintenance times, and tie it to low wind cycles, and literally squeeze every dime out of a wind turbine that you can because, again, as we move towards a subsidy-free world where the PTC expires and we get more, and gas prices stay low, natural gas prices stay low, that's going to be the challenge for this industry is to find ways to make life cycle costs of a unit low such that the overall value equation and pro forma for new units is ultimately benefited. So this is a technology that GE is heavily investing in, and we look forward to sharing this with all of our customers. I guess at the end I'll take questions, but I believe that was my last slide. Yes, it was. So I believe questions are going to be saved to the end. So,
Okay, well,
Nick,
thank you. Thank you,
back
Jeff.
to you.
That was an excellent presentation. Before we pass the mic to Ross, I want to remind you guys that when you are asking questions, if the question is specifically for Jeff or specifically for Ross, please specify. If it is for either presenter, you do not have to specify. And with that, we will pass the microphone to Ross McKellar. Ross, the mic is yours. Ross, I think you're on mute.
Am I coming through clearly now?
Yes, Ross. Go ahead,
Oh,
please.
okay. Thank you very much. My focus today is to talk about the benefits of condition monitoring, how they can, and the cost consequences of implementing a predictive maintenance program, and how they can be, and how the cost consequences are such that you can minimise the cost of maintenance of your turbine. Before we start, though, I think it's important to talk about what the objectives, the basic objectives of a maintenance program are. And it's important to note that we can never, through maintenance, improve the design level of safety and reliability of the equipment. The only way we can do that is by implementing design changes. Now, one of the benefits of condition monitoring is it assists you in achieving a design level of reliability, and also provides you with the information necessary to know what design improvements you should make. The other benefit is it gives you an opportunity to minimise your total cost, mainly through taking advantage or improving availability and taking advantage of resources which you may bring onto your farm and be able to aggregate those across a number of turbines. I'll just change, there we go. So the major benefits of the condition monitoring and the contribution they make to achieving your maintenance objectives is that they will allow you to obtain the design level of safety and reliability within the equipment. They'll allow you to obtain the information necessary for design improvements, and it'll allow you to achieve these goals at minimum cost. and it's important to understand why condition monitoring is important for wind turbines, especially when we consider the remote location of the wind farms, the access issues we have for the turbine drivetrain, and also the failure rates for wind turbines are affected by the site where the turbine may appear within a row on the wind farm, the topography of the wind farm, turbine type, gearbox type, wind regime, controller type, etc. And this is possibly the most important. When you consider a wind farm, all the machines on the project do wear at approximately the same rate. So if you've got an increasing failure rate with time, you'll find that there's a good probability that they'll all strike in a given time frame. So it's important to be able to gain control and know where you're at any particular time. The other aspect of condition monitoring, which is so important, is we're trying to prevent premature failures because the financial consequences are so high. And then when we look at safety, it provides you with an opportunity to mitigate those failure effects, which can have a significant impact on the safety of your turbine, and ultimately it allows you to keep your spare parts costs at an optimum level. What I've got here with Monotech has done some maintenance modelling and taken the information from spin trends, from Frontier Pro Services and our own experiences, and we've attempted to model, and this is an atypical turbine, the brand is not important, but it illustrates how over the lifetime of a turbine your annual costs per turbine can vary. And so you can see that in year 5 and 6 we have a peak. In year 13 through 15 we have a further peak, and 19 and 21 and so on. The blue is our expected costs associated with detected defects, but in this particular case we have a high degree of consequential damage because I'm showing the expected costs associated with a turbine which has got no CME installed. So consequential damage can become quite or very significant, and in some cases be greater than your normal operating costs of the turbine. The goal of condition monitoring is to reduce this consequential damage down to a minimal level, and where you see the peaks within this graph, those peaks can vary again depending on turbine model and the wind regime within the farm and so on. And however, the actual shape of the curve and the actual absolute numbers are atypical of turbines out there which have a similar configuration to, say, a GE or a Vestas machine or a Siemens machine. So if we introduce condition monitoring and we can mitigate the consequential damage, we can have a significant impact on your overall costs. Whereas if you look previously, you'll see that the consequential damage in the worst year, which in this particular case is year 14, your overall costs jump up to nearly $250,000 per turbine. When you introduce condition monitoring, you can drop those down to, in this case, 100,000. So we've reduced it by a factor of 2.5 to 1. And Jeff was talking earlier about the importance of up-tower repair. In order to be able to achieve these sort of numbers, it's important to maximise the up-tower repair, and the only way you can effectively do that with minimal consequential damage is use condition monitoring techniques. And the condition monitoring techniques I want to talk very briefly about today, because there's been many other courses, etc., dealing with each of these, but how they impact the costs on a atypical turbine. I want to focus mainly on vibration analysis, oil analysis, and grease analysis. When we look at vibration analysis, typical sensor locations are indicated with the yellow dots on the figure there, and let me go back. And you can see that we have covered all of the rotational elements of the main drivetrain. We look at the main rotor bearing, and we've got 5 locations on the gearbox, and we've got 2 locations on the generator. And with the vibration, we can detect problems in all those components of the drivetrain with sufficient prior warning, so that you can take effective action without having to getting involved in a consequential failure. Oops. Well, I'll just get this moving on. When we look at oil and grease sample locations, we look at the blade pitch bearings. They're the CM technique, which is particularly appropriate to the blade pitch bearings, is grease analysis. The main rotor bearings is an appropriate technique there, is grease analysis also. For the main gear case and the yaw gear cases, oil analysis is appropriate. And then with the slew ring gear, grease analysis is, is particularly appropriate, without having to remove grease from the gears, so that for visual inspection, the grease gives you a very good indication of what's happening there. You'll note that I showed earlier where we were looking at doing vibration analysis on the main rotor bearing, and also grease analysis on the main rotor bearing. And the reason that we, for the critical items, we should look at as many condition monitoring techniques as we can economically apply. All these techniques have complement one another. And for instance, for the main rotor bearing, as we're all aware, an unplanned failure can be catastrophic, both from a safety and an economic viewpoint. So we should consider utilising every technique that's available to us. And in this particular case, I've looked at three techniques using temperature, using grease analysis, and using vibration monitoring. And with each of these techniques, I've assigned a probability of detection of a defect within the main rotor bearing. And if as you can see, the maximum of any one individual technique can offer is 95% for detection of a defect. However, if I combine all 3 techniques, because all 3 techniques tend to look at slightly different aspects of the bearing, the overall probability using these 3 techniques simultaneously increases to 99.95%. So we can go from 95% up to 99.95% by utilising the 3 techniques versus only the 1. And this applies to all aspects of the drivetrain, or all components within the turbine. If it's possible to look at a number of techniques, complementary techniques, you can significantly improve your probability of detection, as illustrated here. What are the benefits of condition monitoring and how they apply to the wind turbine. We look at more profit through better planning and reduced downtime. And again, that was touched on by Jeff. We're looking at efficient batch crane usage, reduced repair costs, and it allows us to better manage our inventory parts management. And the reason for that is because the condition monitoring techniques provide us with sufficient advance warning of problems occurring, and allows us to practice a just-in-time parts approach. Also, which is most important, is it reduces the risk exposure. It reduces the exposure to unbudgeted expense. It will pick up serial defect detection, serial defects early, and this is especially important when you have your, say, 100 turbines in your farm, all aggregating total time at the same rate. And also, when you consider your life cycle and warranty documentation. A final thought, when you look at implementing condition monitoring system on a turbine, you only have to save one gear case or one main rotor bearing change out throughout the life of the turbine to cover the cost of an online vibration monitoring, and you cover that cost by at least a factor of 10. So when one looks at the cost benefits of condition monitoring systems, and in that I include both online vibration systems and online oil analysis systems, and implementation of grease sampling and so on, you get a tremendous return on your investment. That's all I have to offer. Over to you, Heather.
Thank you. Thank you, Jeff and Ross. I'm sure the audience found that as useful as I did. Let's wrap up with just a few questions from the audience. First question is for you, Ross. What tests do you run for grease analysis, and how much grease do you need to run these tests?
Good question. Normally, we need about 2.5 to 5 grams worth of grease, and we use when we do the grease analysis, we use optical approach. We actually dissolve the grease, and then we separate it out into ferrous and non-ferrous particles, and then we pass it through filter paper, and then we classify the debris both through morphology and density, and we have a schema in place where we classify it in a manner which allows us to trend the changes in the wear particles within the grease. When we're looking at the grease, our major goal is to look at the wear particles within the grease, considering the grease as a carrier of these wear particles. When we don't involve ourselves or do testing to look at the chemistry of the grease.
Okay, thank you. The next question is for Jeff. Jeff, are the gearbox repair costs only based on onshore?
Yes, at least the data that I gave is only based upon onshore right now. I did want to, and I think we have a little time, I want to build upon something Ross said, because he said a couple of things I think were very important and worth repeating. First off, at least by my calculation, Ross, we're pretty close that for a rough 6,600 megawatt wind farm of 66 GE units at least, over the life of the unit, it only takes 1 or 2 up-tower repairs to justify the overall cost of the system. So I just want to highlight, I know the cost of CMS systems have been coming down, at least vibration-based systems have been coming down, and you might want to, for those people that may have looked at it a while ago, might want to look again, because there are also multiple type of systems now coming onto the marketplace, from those higher-end continuous monitoring ones to ones that don't necessarily do continuous monitoring but do pulse monitoring, to even portable systems now which I think the other point Russ made that was good is that there's several different types of condition monitoring, whether it be vibration, whether it be oil particle analysis, whether it be grease analysis, oil sampling, and it's really a strategy of which one of those fit your farm. One customer I was talking to recently putting in an oil particulate detection system, and then once he finds something, using a portable CMS scan and bringing it to the machine for a week was right for that customer. So there really has become a wide range of CMS products on the market now also.
Okay, thank you for that. The next question is, in terms of major maintenance, how has the current gearbox fleet availability compared with the GE 4.1 offshore turbine? What are the pros and cons? I guess that would be for you, Jeff.
Say it again. You want a comparison between the GE 4.1 offshore, which is a prototype unit that has not been sold necessarily, to the 1.5 fleet? Was that the question?
It says, in terms of major maintenance, how has the current gearbox fleet availability compared with the GE 4.1 offshore turbine?
Okay. Well, I don't have a lot of specifics on the 4.1, which was I believe is our newest design right now, and in fact is in prototypes right now. So I can't comment on that, but I will comment on the other part of that question about for the rest of the fleet. Clearly, what we've seen is that the maintenance outage, the failure rates of major components, generators, gearboxes, blades, things like that, and shafts, has been generational. We saw, at least from the GE machines and the machines that were developed shortly after, starting off with the Enron and Zahn machines and Taka machines in the early 2000s, had one failure rate. When we purchased the units shortly after that, they had a failure rate in 2005 to 7 time frames. We saw some changes in that based upon some new technologies. And every couple of years we see newer gearboxes designed and enhancements brought into those designs based upon practical experience that I think has gotten significantly greater confidence in gearboxes in general.
Okay, thank you. The next question is for Ross. Ross, are the cost cycles mostly driven by a gearbox life expectancy of 7 years?
No, when we looked at the life cycle costs, where we were looking at fatigue as the major failure mechanism within the various components, and you'll find that our goal in the application of condition monitoring, as Jeff spoke lucidly about, was to keep the gearbox up tower for as long as possible. So if you attempt to do that, what will eventually force you to remove the gearbox and including the main rotor bearing from the tower would be if you have issues with the planetary section of the gearbox. So ultimately, if you're implementing condition monitoring and utilizing all the tools available to you to maximize up tower repairs, you'll eventually have to remove the gearbox due to the low speed end of the gearbox, unless in the future tools become available to replace those components. And so when you saw the maximum peak there between 11 and 17 years, that was associated with repair of and fatigue failure of the low speed section. The work you do on the high speed section, which will still be replacing high speed gearing, high speed gearing and high speed bearings, they cause the other bumps that you see in that curve that I put on the screen.
Okay, thank you. The next question is for both gentlemen. Are current data acquisition CMS made online or offline? If offline, what's the usual delay between the acquisition and analysis?
If I can
this is Jeff. I guess I'll start.
Oh, but just before we go, Jeff, can you clarify offline, are you talking about a route-based monitoring approach?
This is just a question that a member from the audience asked, so
Okay.
they didn't include any additional information.
Okay, well, I'll assume by offline that they imply route-based monitoring. Okay, so sorry, Jeff, please proceed.
And Ross, I guess I had kind of made that assumption also. And I guess what I was going to say is, again, this goes back to the fact there's numerous varied products now. Clearly, the ADAP system that GE uses right now as its standard system is a continuous-based system, and we are constantly monitoring this, so there's no lag time. We monitor it around the clock through our ROC, and if we get an indication, depending upon what type or level of that indication that is, we either will take appropriate action, starting with an email up to a notification to shut something down. But there are also systems, as I mentioned briefly, that do take pulse data that will monitor for a certain amount of time during the day, and not necessarily be real time. And those are generally reviewed within the 24-hour time frame, at least from the ones that what GE is approaching.
Okay. Firstly, let's address the route-based. There have been a number of approaches applying route-based monitoring where and normally the safety protocols of the various operators prevent a person being up tower while they're taking measurements. So inevitably they would have to run leads from the tower down to the base of the tower in order to take measurements, and with all the time considerations that implies. As from the time that those measurements are taken until you get results, varies on the individuals doing the measurements. Within Monitech, we apply both online or continuous monitoring. We install continuous monitoring systems, and also from time to time we do route-based. And with route-based, we always look at getting reports back to our clients within 10 working days. But with continuous monitoring and the analytical systems that go with them, we can get results to the client pretty well immediately.
Okay, thank you. The next question is also for both gentlemen. What is a reasonable range of added cost for CBM per turbine, including periodic analysis or reports?
Jeff, do you
Ross,
want
I'll
to
let you
start
go first on this one.
Beg your pardon?
Sure. I'll start. The range, the good news is that CMS systems have come down in price over the past couple of years, and I see that trend, while maybe flattening off, start continuing. As I said, there's a range of CMS systems. For a continuous monitoring system, which is at the higher end of at least what I consider to be the product line. If you buy it with a new turbine, it's probably in the range of $6,000 to $8,000 per unit. If you buy it separate from the new turbine and have it installed in an installed base machine aftermarket in the field, it's probably in the range of $8,000 to $10,000. There are other products that can do continuous monitoring, not necessarily vibration-based, that are in the range of oil particle detection systems and things like that can range anywhere from $3,000 to $5,000. There are portable systems that are also much less costly, and I'm not sure how you divide it up by per unit, but they're certainly under $10,000.
Thanks, Jeff. Our experience is for continuous monitoring systems, we see in the price range 5,000 to 7,000, depending on the configuration, the number of points being monitored, and so on. And they can, if one also includes continuous oil monitoring, they can, as Jeff said, can be between $2,500 and $5,000. As far as portable monitoring systems are concerned, the cost there really starts to creep up when you consider you have to move your systems from turbine to turbine. So if after you've allowed for the cost of the portable system, which can be anywhere from $8,000 to $15,000, you're still looking at continuous costs associated with locating the equipment up tower and this style of thing, which can become expensive depending on how you price out your labour. As far as analysis is concerned, a large number of systems, and the systems that Monitech is familiar with, we look at setting up an alarming approach and set alarms to pick up impending problems. And then once we start to see a problem develop, we would then go in and analyse that in more detail and determine whether we should adjust the alarm limit or whether we should take corrective action. As far as Monitech also provides routine reporting on wind farms when we implement systems, and we normally look at providing a monthly report on the condition of the farm, and then if important issues or significant issues are developing, we use email or whatever to advise the client. And also we have systems out there which will advise the client of impending problems without any human intervention.
Ross, is there a cost to that monitoring, an additional cost?
That can range from between $80 and $95. And it depends whether, and it can even drop lower than that depending on whether the client decides to host the data themselves or not. But it would be of the order of between, if the client decides to host the data, it would be between, say, $50 and $70 per month per turbine. And if it was hosted off-site and the hosting cost was included in the analytical services, you'd be looking at between $70 and $95.
Okay, thank you.
You know, one other point Ross brought up something I just want to expand upon. When you get a CMS system, please, it may seem obvious, but make sure you understand who owns the data. And I think with most third-party systems, that's not an issue. But with some OEMs, and thankfully not GE, make sure you understand who owns the data. Because obviously you may want to port that data, you might want to route that data, do other projects with it, use the data for other subjects. So make sure you understand who owns the data.
Very, very, very good point. Very good point.
Okay, the next question is for Jeff. Do you have any data about CMS usage in composite blades? What benefits exist?
Well, at GE right now, I'm not necessarily using any kind of detection systems on the blades themselves. Now, the blades do translate, obviously, into stresses, loads, and other things onto the drive train. But unlike what we were talking about, a vibration system that has accelerometers on the main shaft, the gearbox, generator, and others, we don't have any specific accelerometers or other types of sensors that CMS uses on a blade right now. Now, having said that, we do have another system within GE on most of our units, something called asynchronous load control, or ALC, if you've heard about it, that does take, literally pitch each blade individually and does take readings from the loading on each blade. As to any specific measurements for composite blades, none that I'm aware of, I guess, without getting into into an offline discussion as to exactly what type of data you're trying to get.
Okay, thank you. The next question is for Ross. Ross, how did you determine probability of detection for the main bearing example for the 3 techniques?
Good question. We determined the probability of detection through both our internal experience and the experience from others. In particular, we drew on the experience of Spin Trends and Frontier Pro Services. We've also done sensitivity analyses on those probabilities, and have found that even though that we might be out by plus or minus 5% on those probabilities, ultimately the final result is very, very similar. So we drew on those probabilities basically through our own experience, and Monotech has been in the business of monitoring, of doing vibration analysis and oil and grease analysis for 30 years. So we've been able to draw on that level of experience.
Okay, thank you. And this will be the final question. What CM technique is easiest to interpret? And this is for both gentlemen.
The one that gets it right. Boss, I'll let you take this one. Go ahead, to start with.
Oh, you're very kind. All techniques have advantages and disadvantages. For instance, if you were, and I'll use this, if you look at it from this perspective, if we were looking at, say, online oil analysis for gear case, it will tell you that you're seeing an increase in wear particles. You know, let's think of an oil analysis sensor, which mainly just looks at the magnitude of wear particles, or the quantity of wear particles going through. So what it'll do is it'll track the increase in the wear particles coming through or being generated by the gear case. But the question then arises is to where are those particles coming from within the gear case? And the oil sensor itself can't tell you that. All it's telling you is that you're seeing an increase in wear particles. If you complement your oil debris monitoring, online monitoring, with vibration analysis, the vibration analysis has the capability of being able to focus in on the particular component which is generating the wear particles or developing the defect. Now, which is the easiest? It is obviously easier if you're to just look at a result where you're seeing increasing a number of wear particles because just a single metric. With vibration, vibration monitoring is at the point in development now where there metrics are being developed which give you simple single number responses, but ultimately you would need to do more in-depth analysis if you wanted to get the most from it. So if you just wanted to get an indication of what part of the gearbox or what component, you can set up metrics using vibration monitoring, and then trend those. And then if you want to go and look at it in more detail, you'd have to do detailed analysis. Now, which would be to do the detailed analysis requires a reasonable level of expertise.
I'll answer the question a slightly different way, or maybe I'll answer a slightly different question. I'm not sure. I will say that the easiest to interpret, at least right now for GE, is probably SCADA data. And you might be surprised to hear me say that, but SCADA data is not static data, and it's the time-based reference and using analytics on SCADA data and outlier and anomaly detection and really some of the things that we've done with SCADA data, which is kind of where the first place to start, that we now can see signatures of things. And when we see certain things, certain signatures from a machine in SCADA data, we instantly know, not instantly, but we can quickly diagnose, say, oh, we've seen this. This is an anemometer issue. This is a load issue. This is an icing issue. This is a parameter setting issue, things like that. So I think in terms of that, I would venture to SCADA data. Now, having said that, the one that's going to have the biggest impact on the machine is clearly going to be, at least where we're focused right now, is going to be more of a continuous monitoring type vibration data analysis, such that we can impact all those other aspects of the long-term maintenance costs.
Okay, thank you, gentlemen. Okay, well, we're running out of time. Once again, this webcast will be available for reviewing at windpowerengineering.com. One final message. You can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention. Enjoy the rest of your day.
Thank you.
Thank you.